We graph rational functions. There's going to be a lot of definitions, so if you'll pause the video here and get these definitions, we'll have another sheet of them on the next screen. Here's your second page of notes. Again, if you'll pause to record these before we get to some problems. We'll graph a first example here. When we graph these, to get an actual picture, we're going to use a graphing utility. It's not that important that we construct our own graph exactly from hand. What we do want to do here is for you to analyze what each of these things are. And some of these definitions you may not be familiar with, so we'll go over one at a time with a pretty simple example. First, from the notes, zeros. Zeros are the same thing as x-intercepts. They're the values of x that make the entire function equal 0. So what we can do here is set f of x equal to 0, and then solve. And at first you may think this is going to take a minute to solve, but really when you have a fraction equal to 0, all you have to do is set the top equal to 0. We've already talked about if the bottom is set equal to 0, it would be an excluded value. So if the top is set equal to 0, though, it would make the whole thing 0. So I ignore the bottom completely. I set the top equal to 0. I get that 5 is one of our zeros. All right, so it's our only 0 in this case. So again, to find a 0, you just set the top equal to 0. Go ahead and put that on my graph. Go over here to 5 and put a dot. It's going to cross right here somehow. For my y-intercept, 0 is the same thing as x-intercept. For my y-intercept, I set x equal to 0. So I can think of f of x as being a y here, and just make these two x's each be 0. And the 0 minus 5 is negative 5. 0 plus 4 is positive 4. We have this fraction. It may help us to change this to a decimal. It's negative 1.25. So I know that my y-intercept is negative 1.25. And on the graph, it would be about right here. So anytime you have an intercept, there's a 0 involved somehow. Just whichever intercept you're looking for, you make the other variable 0. Now here we have the word asymptote. Asymptote may not be a term you're as familiar with, and what that's going to be here is a line that our graph approaches more and more closely. And from the notes, vertical asymptote is where we set the bottom equal to 0. It's pretty simple here. X plus 4 equals 0. Subtract 4 from each side. So you get the equation x equals negative 4. Now, why is that a vertical asymptote? Well, we know that negative 4 is an excluded value. So you can't put negative 4 itself into the function. It wouldn't show up on the graph at all if you did. But as you get very, very close to negative 4, the denominator gets very, very close to 0 and causes the value of this thing to either get very, very large or very, very small. So vertical is straight up and down. Make a dashed line through here. Dashed on a graph just means that it's not actually part of the graph, it's just a sketching aid. So what my graph is going to do here, so I'm going to go ahead and graph part of this. I know it's going to go through these two. It's going to get very close to that line, but I'm not able to touch it because it's an excluded value. And as it goes down here, it's going to get very, very close to it, but will never actually equal that. And on the other side, it's going to go the other way. It's going to get very, very close to it this way. I'm going to show you what happens here in just a minute. But again, vertical asymptote, you just set the bottom equal to 0. Horizontal asymptote depends on the situation. You saw the notes there. This is the case to where my degrees are the same. If my degrees are the same on top and bottom, the horizontal asymptote is just the leading coefficient divided by the leading coefficient. In this case, your two leading coefficients are each 1. So if we take 1 and divide it by 1, of course, that's going to give you 1. So my horizontal asymptote is y equals 1. The reason we say y equals is because if you'll remember, when you graph lines, y equals makes a horizontal line. So I'm going to put a horizontal asymptote right here at 1. And now we can see that this graph is going to, right here is going to start to dip down. It may go out of the picture here, but it's going to get very, very close to this line, but we'll never touch it. Same thing over here. Very, very close to this line and not touch it. And yeah, I don't expect you to be able to graph this perfectly just from this information, but we do want to be able to analyze each of these pieces. Now, a quick reason why this horizontal asymptote, why does that work here, was x gets very, very large, this -5 and this 4 become less and less significant, and the ratio between these gets closer and closer to 1. So as your x gets very, very large, this is getting closer and closer to 1. Finally, domain and range. Domain is easy. If you've already calculated your vertical asymptotes, domain is just simply going to be every number except whatever my vertical asymptote number is. So here we can say all reals except -4. Because if it equaled -4, I'd have a 0 on the bottom. All right, so if you've calculated your vertical asymptote, the domain would be every number except for that. Sometimes you do have more than one vertical asymptote. Here we have only one. Now range, it depends on the situation. You really have to graph it before you know the range. Range are all y's covered. So in this case, you can see it goes down forever, it goes up forever, but there is one point that it can never be, and that's the number 1. This will never have a y value 1. So we say our range is all reals, make it plural, except 1. If you try to set this equal to 1 and solve it, you're going to find that it's impossible for it to equal 1. Another example here, we could take a graphing calculator and graph it right away. And a graphing calculator that I recommend online is desmos.com, desmos.com. Don't feel like you need to go out and buy a graphing calculator. That's not the case. We can check one out to you when you get back. But you probably can download one on your phone as far as that goes. But I'm going to wait to graph it just so we can see all these things come into play here. Zeros, again, makes the entire function be 0. So I just set the top equal to 0. It's pretty easy to see that it's 1 here. Zeros are x-intercepts, so we'll cross right there. Y-intercepts, it's going to be when I plug 0 in for all the x's. If I do that, the only thing that's going to be left, I'll write it out here, but the only thing that's going to be left are your constants, the numbers without the zeros in them, or without the x's in them, I mean, because zeros are going to go in for the x's. So it ends up being, in this case, -1 over -8, which is the same thing as +1/8, which is going to be just barely above the origin here. This graph is going through here somehow. Now for vertical asymptotes, we set the bottom equal to 0, so we might as well go ahead and factor it. Because later on we're going to see something called holes in the graph, which doesn't happen here, but we need to graph it to see if it's an asymptote or a hole in the graph, because they're similar. Now let's go ahead and graph it here. So this is going to be x minus 4 and x plus 2. And just to preview the holes in the graph, that would be if something canceled out. We'll talk about that more later, but that doesn't happen here. My vertical asymptotes are going to be at 4 and at -2. Same numbers that would be your excluded values. I have 2 of them here. -2 and 4. Right through there. A horizontal asymptote. If a horizontal asymptote, it's best to look at the original problem. This is the case to where the degree on the bottom is bigger than the degree on the top. So if you look back at your notes, that would be a horizontal asymptote of 0. So 0. Right through here. All right, so we'll take just a moment here and graph this. We'll go ahead and graph it now. When we graph it, what I did was looked at my graphing calculator to make sure that we had it going the right way. And the only way you can get a good graph without a graphing calculator is to make an extensive table of values, which is not very helpful. It's not a big skill to do that because for the most part throughout the year you don't have a graphing calculator. Again, online, there's different places to find it. Let's go ahead and graph it. What happens here is I have a piece of the graph which does this. You're never going to touch the vertical asymptote at all. And on the ends, you're not going to touch the horizontal asymptote. The other corner does like this. Again, staying away from both asymptotes. And the only way I knew it was there and there is I graphed it. And on the middle piece, it must go through these 2 points. So what it ends up doing is this. Again, never touching the vertical asymptote, but in the middle you do sometimes cross the horizontal asymptote. It's on the ends to where the horizontal asymptote will not be touched. If there's 3 pieces, the middle piece will cross it. So graphing calculator, Desmos.com is a good resource. There's other resources you may like as well. Let's finish this up also, domain and range here. The domain is everything except for our vertical asymptotes. All reals except for -2. And from our range, you just have to look at it. It goes down forever, it goes up forever, and on the ends it doesn't touch 0, but it does touch 0 in the middle. Okay, so range here will be all real numbers. We'll do another video in just a minute to add a couple more examples.